Ladies and gentlemen, the afternoon session will start after 3 minutes. Please be seated. 各位贵宾，我们下午的议程即将开始，3分钟后即将开始，麻烦请陆续回到您的座位，谢谢。
那个下午很快就开始了哈。我是詹前登哈，我是来自成功大学。My name is Chen Den Jian. I'm from the National Tsinghua University in Tainan. It's not far away from here. In some part, if you take the high-speed train, maybe in 2 hours. Used to be 3 hours, but right now, today, I just take about 2 hours from Tainan to Taipei. Not far away. In this section, we will have 4 speakers. I think we follow the same style like this morning. So after the speakers present their presentations, then we will have discussion sections. So each one about 15 minutes, I think so. Okay. The first speaker, 我们第一个演讲者哈，刚刚有地震对不对哈？这样第一个演讲者他就要讲地震。Our first speaker, Margarita Dizon, we're talking about the earthquake. Because today we just have an earthquake, even though one is not so big. Okay. But this one will be very big in 2017. So she was talking about the spatial distribution and assessment of earthquake induced by landslide. Let's welcome the Margarita Dizon. Okay, let's give her a big hand.
Good afternoon, everyone. I think there's, did you feel the earthquake earlier? I think that's the best introduction for the presentation for today, for my presentation. So I'm Margarita Dizon from the Philippine Institute of Volcanology and Seismology. I'm focused on my work on the earthquake-induced landslide hazard mapping. Then, for today, I'll be presenting to you the study we did, or the research we did for the spatial distribution and assessment of the earthquake-induced landslide triggered by the July 6, 2017 magnitude 6.5 earthquake in Leyte, Philippines. This study is part of the QRT, or meaning it's a quick response team work. So meaning it after the earthquake, we immediately deploy in the area and do the field mapping, assessment, interviews in the community and in the other areas that are affected by this earthquake. So this is a group work. So I'll be, in behalf of my team, the QRT team from the FIVOX. This is the presentation. Okay. So next. So the presentation is guided by the following outline. So first, I'm going to discuss the scope of the study, then the Leyte and its hazard, then the event. It's a more of introduction. Then I'll be showing you the QRT fieldworks that we had made, and also the utilization of the more remote sensing technologies. And then later on, we did the data integration and analysis for this particular earthquake event. Then we have the summary and the way forward. So the scope of the studies is to study the relationship of the landslide distribution with geology, topography, and distance from the epicenter triggered the magnitude 6.5 earthquake in the Leyte. So aside from the proximity of the earthquake source, we know that the other factors that may contribute for the landslide is the steepness of the geological material that failed. Then, next scoop is the distribution of this earthquake-induced landslide will help to understand the mechanism and assess the landslide-prone areas in Leyte. So part of this scoop also we did is the first time we did the inventory of the landslide from QRT mapping, and at the same time with the interpretation using the satellite imageries. Where I will not give details for that, so we will just state that we did the inventory for this particular landslide event. Then, lastly, the distribution of this landslide will serve as a validation of the existing earthquake-induced landslide EIL hazard map produced in 2007. Then the sources we use are the QRT field mapping data and the UAV surveys, or the unmanned aerial vehicle survey we did in the July 7 to 22, 2007. So that is the very short span of the observation during the earthquake event. Then we have used the geological maps from the other National Institute, or the MGB, or the Mines Geoscience Bureau. Then for the identification and location of the landslide, we use the PhilGIS data. And for the interpretations of the landslide, for the identification, we use also the worldview satellite images provided by the our sister agency, which is the Advanced Science and Technology Institute. So the data used for the interpretation is only from July 7 to 22 also. Then we use the IFSAR data for the digital terrain model, and we utilize also the Google Earth for the multi-temporal images, so we can compare the pre and post event imageries. Then for the processing, we use the environment for visualization images, or the ENV, and for the data integration, we use the ArcGIS. So these data are all integrated and plotted using the ArcGIS. So Leyte, province, and its hazard. So that is the main focus of the landslide, the research. So here is the map, is the province of Leyte. It's overlaid in the slope map, and this one is the province of Leyte overlaid with the geology materials. So Leyte is found in the central parts of the Philippines, so in the Visayas area. So it's composed of mountainous area at the central part, and the slope is to the 88 degrees. Then using the IFSAR, the elevation range can be range up to 1,250 above sea level. Then the general geology is mostly consists of highly and weathered volcanic and sedimentary rocks. Rocks are poorly or moderately indurated, fractured due to folding and faulting with thick layer soil. No? We assume that the landslide that are situated in these highly weathered rocks and materials are possible for a landslide, for failure, for slope failure. Then, so Leyte has a lone source for earthquake generation. So this is the Philippine Fault Zone. It's 140 kilometer long, and the latest segment, which in this part, is the one that generates the magnitude 6.5 earthquake. So it's characterized by linear and valleys and upstreams and offset streams, hillside ridges, and wind gaps. Large portion of the sleep is accommodated by the creeping based on the field observations and INSAR analysis. So in the northern part end of the Leyte Island, you can see there's a creeping movement here in this part. Then this part, at the southern part, there's a parallel fault traversing the mountainous area of St. Bernard. If you are familiar with St. Bernard, there's a 2006 big landslide disaster that happened there, the Ginsagon. Then based on GPS, there's a slip rate of 2 to 2.5 centimeter per year, and can produce mild to moderate earthquakes. Then, as we know that there's always a generator for the earthquake in the area. No? For the seismicity, we can see that this is the Leyte province, this is the Leyte Island, and in its vicinity, there's a lot of earthquakes that is happening in the area. So based from the Box catalog from 1600 to 2017, there's a small to moderate magnitude earthquakes that happen. Then there are also recorded significant earthquakes in Leyte Island. In the 1994, there's a magnitude 6.2 here in the south of the Leyte Island. Then there's in 1947 magnitude 6.9, and 1890 magnitude 6.5 and magnitude 6.1. In 1863 here in the part of Leyte. Then there's a series of earthquake swarms in this southern part of Leyte also. So there are earthquake swarms in 2012, 2007, and 1998 to 1994, then 1991. So earthquakes range from 4.3 to magnitude 4.3 to magnitude 5.5. So given that the Leyte is very active when it comes to seismic activities. So in 2007, Leyte was prioritized to produce earthquake-related hazard maps. This map is under Ready project in 2007. It is composed of the ground rupture, ground shaking maps, tsunami hazard map, liquefaction map, and earthquake-induced. And earthquake-induced landslide hazard maps. So these maps are being distributed to the public, the local government unit, during the education information campaign, and also available in the FIVOX website. So you can download this also. So for the earthquake-induced landslide map, it is modeled based on Newmark method of sliding block analysis, and this is also a determinist. It is modeled in a deterministic hazard assessment, and hazard assessment level in the map consists of high, moderate, and low stability, including the identification of the depositional zone. So the level in the hazard are reclassified based on the accidents map by comparing the critical acceleration and the PGA acceleration. So that is the seismic acceleration. Then this is the magnitude 6.5 earthquake. It is produced by the movement of the Philippine fault, the Leyte segment. So you can see the intensity is concentrated, the high intensity is concentrated in the elongation of the fault. The highest intensity is intensity 8, and farther from that, the neighboring provinces experience also, but then in a lower intensity. So for the focal mechanism, the Leyte segment reveals a left lateral strike with a strike of 234, and with a dip of 85 degree, and with a rake of negative 159 degrees. Then also, we have checked also the aftershock distribution in the area. So in Leyte, there's a recorded 1,023 small to moderate magnitudes aftershocks, ranging from 1.5 to magnitude 5.8. So during the QRT, the Philippine Fault Leyte segment, this is being mapped, which is about 26-kilometer rupture with the highest displacement of vertical displacement of 1 meter and horizontal displacement of 0.5 meter. Sorry, I interchanged the value. And these ruptures are evident in this area. For an example, now this is a mountainous area, but the rupture occurs in the foot of the slope. So this one. And also, some ruptures can be seen also in the top of the slope. So this one is an example of the landslide, and you can see the black lines are the scarp of the landslide. So based on we compared the result from the from the ground and also the remote sensing image. So it's coincide with the length of the deformation using the DINSAR. Its result coincided with the geologic impacts of the later earthquake. This DINSAR analysis, you can see the deformation where the massive landslides are happening. Okay. So for the field survey, sorry, I will speed up. So for the earthquake, so these are the field pictures during the mapping. So you can see there's a landslide here that threatens the community of Barangay Tungon, and there's also a block of roads, and also the incipient landslide in this area. Oops. So the also this landslide result to the displacement of many residents. Then the landslide impacts is another example of landslide impact. It's this is 70 houses collapsed and damaged in this part and the ridge crest. Then this is the area also that there's one fatality due to the collapse of the building. And of course, there's a mass evacuation. Then another example is that the tension cracks appear on the plateau of the area and damaged houses near the crest or near the hill, the end hill. So yeah, and there's also road blockage. So earthquake-induced landslide impacts also observed in the houses that are built on the steep slopes, and also there's some debris flows from the area that some landslide deposits transported to a channel overflow of the river. Sorry. So the distribution of the earthquake landslide on site is counted as about 145 landslide. So these are the observed landslide in the area, and these are the locations. And about landslide are normally occur in the highest with geologic material of andesite and basalt flows. Then for the hazard, all landslides are coincided with the landslide hazard. Then there's another, this is for the aerial interpretations for the distribution of the earthquake-induced landslide. About 669 landslides are identified. And also these are coincided with the PVOX SD Ready project hazard maps. So this one example of the landslide in polygon and point and located as point from the previous map. So some analysis for this is the map of earthquake-induced landslide distributed relative to the earthquake intensity. So you can see the concentration of the highest intensities in this area. And the landslide occur in the intensity magnitude 5 and above. And the landslide mostly happen in New York City. Then for the map of landslide distribution relative to proximity from the epicenter and the latest segment, so mostly earthquakes are concentrated 12 kilometer from the epicenter, 12 kilometer distance from the epicenter, and from the fault it's concentrated up to less than 10 kilometer from the fault. Then the landslide mostly happen into 500 to 750 meter elevation. So for the landslide inventory, landslide identified mostly falls in the marine and submarine and andesite or basalt flow of the geology. Then we do the hazard analysis for this area. For about 669 landslides are also coincided in the hazard map. And we can see also in the slope, if we considering the slope of the centroids of the polygon, the normal slope range is above, mostly is 20 to 33 degrees, the highest peak. But if we consider the highest elevation of the peak, it's normally the slope range is between 76 to 31 degree. Then for the summary, based on assessment, landslide occurred triggered with a magnitude 6.5 earthquake are within the 2007 Ready Project EIL hazard maps. The magnitude 6.5 later earthquakes-induced landslide events, mostly at a slope failure up to 60 degrees, with elevation between 500 to 1,250 meters as the highest susceptibility. Landslide occurred mostly on moderate to steep slopes in areas with intense shakings or along or near ridges and on highly sheared and unstable geology. So this indicates that the wave interaction with complex topography caused ground shaking amplification. So okay, for the summary, again, it's the landslide distribution from the fault is nearly 10-kilometer distance on the both sides of the latest segment and up to 12 kilometers from the epicenter. So for the way forward, so we envision that for further analysis for this, we think that it's better to conduct an on-site geotechnical data to better understand the failure mechanism of the slope to support numeric method and additional ground-based inventory of landslide and satellite-based images, and also update the EIL hazard maps based on later event and the latest available data sets. And that's all. Thank you. Sorry, I speak very fast.
Yeah, thank you very much. Yeah, we can keep it easy. 我们问题还是一样，移到那个等一下结束再一起问哈。Thank you. Our next speaker, 方耀明博士吧，方博士哈。Okay, our next speaker, Dr. Fang from the Fengjia University in the central part of Taiwan. He was talking about the debris flow monitoring system in Taiwan, a case study in Yuzhi River. Okay. So, are you ready? Okay, once you're ready. 你要这个吗？ you have one. You have already. 先放这里。
Good afternoon, ladies and gentlemen. I'm Yao Ming Fang from GIS Research Center. It's my pleasure and honor to be here, have a presentation of the debris flow monitoring system in Taiwan, a case study in Yuzhi River. My presentation will start from to introduce the debris flow monitoring system in Taiwan, which established from the Soil and Water Conservation Bureau. Then I will discuss about vibration signals of debris flow, and then we'll use a case study in Semu village to illustrate the characteristic of debris flow monitoring signal. This figure shows the development of the debris flow monitoring system in Taiwan since 2002. Up to now, the Soil and Water Conservation Bureau construct 25 permanent stations around Taiwan, which 21 for debris flow, 3 for sediment concentration, and 1 for landslide. Since 2003, the Soil and Water Conservation Bureau has developed 3 mobile monitoring stations and continue to implement, upgrade the item of the mobility and functionality. After the Typhoon Morak, the Soil Water Conservation Bureau has developed 17 portable units and continue to upgrade the weight reduction. Since 2014, there are 61 automatic weather stations constructed in a high mountain or in a high risk area. The debris flow monitoring system in Taiwan include monitoring network communication, sensors, and monitoring software. There are 2 types of sensors. One is called direct method sensor. which include like the geophone and still well sensor, which can actually tell the debris flow occur. Another type of sensor is indirect sensor, direct method, which including the sensor like the rain gauge and the CCD camera. These are like the environmental sensors to collect the size of the data. Like the rain gauge amount of the sensor is very important index about the warning system. Another sensors like the soil moisture sensor or the water level meter will depend on the site, the needs of the site. These are our research case study in Senmu village, located the Ayutz River, and this area the river occur frequently in the past years. This slide shows the information about the Senmu area. There are 3 high potential torrents in this area, like the Ayutz River, Chushui River, and Hosa River. From the satellite image, the landslide area in the upper stream of the Ayutz River was larger than another rivers. So, depend on the environmental condition of the area, the river usually occur at the Ayutz stream in the past few years. This slide shows the layout of the monitoring station in Senmu village. As you can see, there are still well sensor and geophone are installed in the river channel, and all the sensor data will transmit to the operation center automatically. This whole system designed and operate automatically 24 hours, 7 days by the local power, and up to 3 days by its own backup generator. Okay. This slide shows the video of the debris flow event at the Ayutz stream on May 20th, 2014. As you may know that the CCD shows the debris flow occur, and the left side shows the vibration signals from the geophone. So there is a still wild sensor will break by the debris flow. Okay. This is a typical geophone record like this one. And there are 3 axes XYZ of the vibration and signal process and transmit to the operation center. And there are 2 type of vibration detect used in Senmu area. One is geophone, another is broadband broadband seismograph, which is sensitive to lower frequency to 0 to 20 hertz, and detect frequency up to 240 hertz. In this study, the signal analysis will use fast Fourier transform and short-time Fourier transform, and also use energy to analyze all the sensor data. Between 2011 to 2014, there are 7 debris fall events in the same area. So we use there are 3 most events about 2 heavy rainfall event and 1 typhoon event will use the sensor data to analysis. This slide shows the result of the time sequence of the vibration signal of the 3 events, and measured by the geophone. The right side we use a wavelet transform to separate the different part of the frequency domain. It is obviously to find the signal peak from the original data. Based on the experience, the ground surface vibration was obviously highlight in the time sequence of the 0 to 31 hertz, as shown the right side. And it conduct that the characteristic frequency of the debris fall in some area is within a range of 0 to 31 hertz. We also conduct FFT on the signal. Here shows the result of the 3 events, both of the geophone and the broadband seismograph sensors. It's obviously to know that the frequency of the 0 to 40 hertz here and the 0 to 30 hertz is significant. Clear peaks are found in this area. The result of these results are similar other references in a research study, so we can focus on the frequency range 0 to 40 hertz for the debris fall vibration signal analysis in this case. This range is considered as a vibration signal characteristic of the debris fall in some area. This slide shows another way we call the spectrograph of the vibration signal. Its intensity of the frequency will highlight with the colors. When we put the occurrence of time of the debris fall with the figure, it is noted that the vibration signal behave the intensity when debris fall approach to the local of the still wire sensor. In some case, the vibration signal of the lower frequency 5 to 10 hertz becomes strong and will detect minutes earlier than the arrival of the debris fall. This result indicate that the vibration signal potentially can be identified as the debris fall event. In addition of the Fourier transform, we also perform the short-time Fourier transform. We use a Gauss window. From this result, as shown this slide, we can illustrate the contribution of the frequency with the intensity and time. This one. It is clear to see before the debris fall arrive the location of the well sensor, then will lower frequency detect few minutes earlier in the figure. These funds imply if we can properly lay out the geophone or the broadband seismograph sensor, maybe capture the debris fall of the debris fall early before it arrives the location of the people living. So we can warn to people to escape from the debris fall. Another way study we use energy to estimate the scale. This slide shows the energy time sequence estimate from the signal of the geophone. By drawing the accumulated energy, the curve shows jump to a slope, indicate the arrival of the front end wave of the debris fall. The energy plot will be used to signal analysis to help determine the occurrence of the debris fall. This front end signal of the debris fall, as mentioned in the previous slide, the front end of the debris fall contain bigger rock here, bigger rock and debris, which generate the low frequency vibration, and we use this characteristic. The signal analysis can find out the front end frequency, as shown this here, front end. In this slide, we can use a lower vibration frequency to detect by the broadband seismograph, and was usually captured a few minutes before the debris fall arrived the well sensor. This slide shows the result of the upstream by the geophone and downstream by the broadband seismograph. For this case study, the typhoon similar in 2013, we compare with the different kinds of vibration signal. The signal time sequence indicate that a time window about 5 or 7 minutes was available before the debris arrived at the village. The time window shows here is available for disaster evacuation. It is then the idea how to extend the time window by using the geophone and the broadband seismograph of the debris fall response. From this study, we conclude that the frequency range of 0 to 35 Hz was suitable for debris fall detection, and the low frequency 0 to 10 Hz may be potentially good for debris fall warning for this thermal area. The seismograph and the short-time Fourier transform were useful to process vibration signal in order to evaluate the contribution of time and frequency with time. It was noted that the energy of the signal will helpful in determining the transition period before the debris fall to arrive. By good design, a layout of the vibration signal sensor and time window can be created to issue of the debris fall warning for the living of the downstream area. Finally, the direct method of the geophone and the broadband seismograph was practically promising for the debris fall monitoring. Thank you for your listening.
Okay, thank you, Dr. Fang. Okay, the next are the third speakers. Jenny Lin Padronis from the University of the Philippines. She was talking about the parameters used to landslide analysis. Okay.
Thank you, Dr. Jan. So good afternoon, everyone. I'm Jen, and I would like to share with you the result of preliminary result of the study that we are doing related to the evaluation of parameters for landslide susceptibility assessments. So probably you're really familiar now with the tectonic setting of the Philippines. So it is located in this area. And shown here is the map showing the catastrophic landslides from 2002 to 2017. And we can see here the yellow lines are the rainfall-induced landslides, and the blue ones are the earthquake-induced landslides. So the study area is located on the western part. We have two study areas here. the Laguna in Mindoro, and note here that there's one earthquake-induced landslide in Mindoro Island. So, as you have noticed earlier, there are a lot of yellow points, which refers to the rainfall-induced landslide, and we can attribute that with the meteorological setting of the area, which is basically mostly rainy period. So, the map shows the different types of climate. So, basically, we have two, dry and wet, but if you look here, we have categories of those dry and wet seasons. So, if you look at the green one, basically it's just wet and wetter, so there's no dry period for the green one. But in the study area, we have two pronounced seasons, the dry one, which is from November to April, and the wet season from within the rest of the year, but there's a maximum rainfall during June to September. And in these study areas, there are few typhoons that have landslide occurrences. So these are Typhoon Zangsan, the Typhoon Ramasun, and Typhoon Kanon. So these are some of the landslide causative parameters that were usually used in the landslide susceptibility assessments. And most of these, the highest frequency ones refers to slope, angle, lithology aspect, and elevation. So for this study, we have used those four, and including land use, vegetation-related index, also structural or lineaments, soil, and distance to roads. So the study utilizes analytical hierarchy process, which was described in detail by Dr. Ramos earlier. So basically, we have used a similar assessment tool, and we have also integrated the weights of each parameter or the final ranking in the GIS platform. So the AHP is very subjective in nature, and thus there's a need to evaluate the parameters that we are going to use for the AHP analysis. So we can see different landslide susceptibility maps because of the difference in the opinion of the experts that are using this analytical hierarchy process. So in this evaluation, we have compared two areas with different geologic makeups. So these are the ophiolitic and metamorphic terrain of Northwest Mindoro and volcanic terrain in Mount Makiling. So similar to the study area shown by Dr. Ramos earlier. So we have also evaluated two causative factors, geology and soil physical properties. So the first study area is located in the northwestern part of the Philippines, and we can see here a red line. In this denotes the boundary of the continental area in the Philippines. So this basically is a stable block wherein in Palawan Island there are no earthquakes. But we can see in Mindoro there are some earthquakes because of the Manila transubduction in this area, and also it is within the collision zone. And the Mindoro area is composed of ophiolitic rock units represented by these basalts and ultramafic rocks. And then it has metamorphic rocks, which are the schist, and sedimentary rock units. So this is the landslide susceptibility map for the area, and the parameters or the factors that we have used are lithology, which has the highest ranking, followed by slope and elevation. We have utilized distance to structure and distance to magnitude 5 earthquake or greater than magnitude 5 because of the fractured nature of the rocks which are nearby those past earthquakes and nearby the lineaments. So here are some examples of the landslides in Northwest Mindoro. We can see here very bare area, which is the ultramafic rock, so it's mostly grassland, and a very thin soil cover. And there are also a lot of landslide in road cuts, and we can see sandstones that are daylighting the slope, so this one. And mostly rock falls in the metamorphic rock. We have assigned highest weight for the lithology. So this is one of the illustration for that. So we can see here a steep slope in the amphibolite unit, which is schist, and these are metamorphic rocks. And this very steep slope is not really susceptible to landslide because of the rock unit in the area is mostly still fresh and mostly not weathered. So we have assigned higher weights for lithology compared to slope. So please also note that there are thin soil covers, so we didn't utilize or we didn't use the soil as one of the parameters. So for the Mount Makiling area, it is quite different. So the Mount Makiling is a potentially active stratovolcano, which is mostly composed of andesitic and dicitic rocks, and you have here debris avalanche deposits, so lahar deposits in this side, and some young volcanic elastic sediments. So this is the landslide susceptibility for the Mount Makiling area, and you can see here some of the parameters were different. So we have assigned higher percentage for slope, which wherein you can see a lot of landslides occurring in a steeply sloping area, and we have included soil because of a very thick soil cover for this area, and some of these are affected by the hydrothermal alteration, so they have been altered into clay minerals. So we also didn't utilize distance to lineaments and distance to past earthquakes because of very few or very small amount of earthquakes that have epicenter around this part and few lineaments. So instead we use distance to river and distance to past landslides. So here you've seen this area picture earlier. So there's a landslide at the Mount Makiling Trail in between station 16 and 17, so this is the previous trail, and these hikers are the one who have reported the landslide, who were the first to report the landslide. So we went to the area and gathered some of the samples, and we also did evaluation along the trail. So we have observed several landslides. So this one is probably during Typhoon Milenio in 2005, and these are other shallow landslide which has occurred in the area after the October 2017 landslide. So the landslide exposes lithologies or rock materials that has not been previously reported for this side of the Mount Makiling. So this is the andesite which was in the geologic map. So this is the only lithology that was in the geologic map, and the landslide exposes this pit layer, the sandstone layer, which is probably pyroclastic flow deposit and lahar deposits in these areas. And since we have used secondary data for the landslide susceptibility assessment, we have recognized the need to validate the data that we are using. So probably most of the lithologies that were reflected in the geologic map were surface lithologies. So we should, for areas like Mount Makiling, which are composed of volcanicastic materials, I think we should also check the lithologies at the underlain by the surface lithology. So we have collected soil sample along the Mount Makiling Trail, and as you notice, we have also collected soil sample in the landslide area. So even though the materials show the original rock material that are there or that are exposed in the area, most of these are mostly in soil. So there are we were able to do some soil texture analysis for these samples. We also compared soil texture for different soil horizons, such as Horizon A and Horizon V. And we can see different soil texture for both of these areas with different lithologies and soil texture difference between horizons A and B. And if you look at the soil texture map that we have used for the landslide assessment, we can only see that these are mostly soil type that are very generalized, and some other, especially for the location of the landslide in October 2017, it's written as undifferentiated. So we cannot put any physical properties for an undifferentiated soil type. So this evaluation showed that there is a need to devise a way in how to reflect the soil texture and other physical properties in the map that we are using for the landslide susceptibility assessment. We have also analyzed the Atterberg limits, particularly the plastic limit and sticky limit of the soil samples. So the red ones are for the samples from October 2017, And we have categorized active, inactive, and no landslide areas. So basically, we can see here higher plastic limits for the areas without landslide. And if you see here the landslide slurry moisture content, this is the muddy deposits during the debris flow in October 2017. So the moisture content or the plastic and sticky limits of the mudstone and tuff sandstone in the landslide area exceeded that of the moisture content. So this moisture content exceeded that of the plastic and sticky limits of these rock samples. So these are probably the rock samples that have failed during the landslide event. So we have also compared moisture content for plastic and sticky limits with clay content. So this shows sandy texture, loamy texture, and clay texture. So the pit sample has higher plastic and sticky limits. So we can see increasing Atterberg limit values with increasing amount of clay content. So with this data, I think we can now factor in the moisture content or the Atterberg limits into the soil textural map. So we can better put weight or ranking for the soil texture factor. So, but there are not no distinct difference for the liquid limit of the samples. So here is the plasticity index, which basically shows the type of plasticity behavior of the sample. So we have clays with low plasticity, and this one is a silt from the mudstone sample, and this one is the organic soil or the pit, but still with low plasticity. And if we look at the different Atterberg limits, if the moisture content is lower than that of the plastic limit, so the soil sample is semi-solid, so it behaves or it will crack or crumble with that amount of moisture. But if it is within the plastic and liquid limit, so the soil sample has higher shear strength. And if it exceeds the liquid limit, so the soil loses its strength and it will flow like liquid. So we have also utilized the plasticity index to determine the type of clay, which are mostly inactive or non-expansive. So these are not the swelling or shrinking type of clay, and these are mostly kaolinite and illite. So that would be all. So for the highlights of this study, so we are still going to continue this study. So for the lithologic unit, we can see influence of the geology in the susceptibility of the area. For the soil parameter, we recognize that the soil texture varies between horizons, so we need to devise a mechanism to incorporate the soil texture changes into the existing or the existing soil texture map. So we also recognize that Atterberg limits has influence in slope failure. So maybe we can integrate this into the existing soil texture map. So this study results show that there is a need to evaluate the parameters such as soil and geology and GIS-aided landslide susceptibility study, and to further refine the AHP analysis and to reduce the subjectivity of the AHP analysis. So that would be all. So thank you.
Yeah, thank you. Thank you very much. And in this section, the last speaker, Zhang Weiyi, Professor Zhang Weiyi, he was talking about the combination of S and C band radars in rainfall forecast. So let's welcome the Professor Zhang. Yeah.
Thank you, Chairman. Good afternoon. So this morning we have heard about the Central Weather Bureau working on the QPF, which is the weather quantitative precision forecast. And now I'd like to talk about the QPE, which is the quantitative precision estimation using radar. So CW already have a very robust system called QPE SANS. So I'm going to talk about for the future work we might be able to do in terms of to improve the QPE in Taiwan. So what is QPE? So any radar-based algorithm we call radar-based QPE algorithm. So traditionally we use the reflectivity measurement to estimate rainfall rate. With the polarimetric radar capability, we now be able to use the ZDI measurement, which is essentially the information of the raindrop size, to improve the rainfall estimation. The reason why we want to use the radar compared to the rain gauge is because the radar can have better spatial resolution and much better coverage. So if we take a look at the rain, if we took the composition of rain, it essentially is a different size of raindrop with different concentration. So mathematically, we can use a normalized gamma distribution, and using two parameters, which is the mass weighted diameter and the normalized intercept, to describe your raindrop size distribution. And for this raindrop distribution, it actually tells a lot more than just rainfall rate. It also tells you the reflectivity factor, which is the radar measurement. It also tells you the rain kinetic energy, which is a very important factor to induce the landslide. And the DSD actually determined by the rainfall process. Different type of rain will have a different process. When we talk about the process, it means a microphysics process. Within the rain, you can have a different phase, liquid phase and ice phase change in between. So the condensation process, glitching, coalescence, breakup, aggregation, global meltings, all these complicated process in the end to the surface give you the surface the drop size distribution. Give you some idea about how the precipitation process will affect the DSD. So this is an example that's showing the height of the echo top of the precipitation. That means how strong your precipitation. If you have a very strong convection, you will have a larger DM value. DM value means the mass weighted diameter. That means you have a bigger raindrop. So imagine you have a rain event, have a bigger raindrop, you give you stronger kinetic energy. You can imagine that in the summertime you have a thunderstorm, you have a big raindrop, but in the wintertime you have a cold front precipitation system. The raindrop usually is very, very small. So now we know that the DSD is determined by the microphysics process, and they all relate to the accuracy of the QPE. So it's quite important to understand the DSD variability. So the way how we usually do that is we try to use the ZDI measurement, as I introduced before, from dual polarimetric radar to give you the information of the size. So, however, that doesn't actually solve all of the problems. So even though we know the size of information, still we have trouble to provide accurate QPE. The main reason is because still the DSD variability is too strong from season to season, from case to case, even within one case. So in the future, the radar network of Taiwan, we are going to have a 13 operational radar, C-band, S-band, Doppler, or dual-pol radar. And we're going to have a 4 research radar. So it's quite important to understand how to combine the advantage of C and S-band polarimetric radar QPE, and it will become an important issue. So because in the central part of Taiwan, we have a mountain, so we need all of the radar around the mountain. So when we talk about the C-band and S-band, that means the frequency of the radar. The reason why we try to have 2 frequencies is because the C-band radar is cheaper, S-band radar is much more expensive. But there's some trade-off. If you take a look at the pro and con of S-band and C-band radar, the S-band radar have a less attenuation effect and wave radon effect. Attenuation effect means when the radio penetrates the precipitation will absorbed by the rain, so the return signal is weaker. So that in that case, you will underestimate your rainfall rate. So S-band has less attenuation issue and wave radon issue. Wave radon means if you have heavy precipitation around the radar, there's a water coat around the radon, so that will also give you additional attenuation effects. So S-band has less issue of that. But for C-band, because the shorter wavelengths usually have a stronger attenuation effect, you have a much problem of these 2 things. And in terms of the ZDR measurement, which essentially give you the size of the information, this is very important because this measurement, even though cannot give you the QPE value, but give you the information about the size and further improve your QPE. So this variable need to combine with the ZH or add the third one. So for the S-band, the ZDR measurement is less noisy and less attenuation effect and less wave radon effect. For C-band, you have stronger attenuation effect and much more noisy. Excuse me. So for the KDP, which is the third measurement, is a phase measurement. So the phase measurement has you don't have to worry about the attenuation effect because it's a phase measurement. Essentially use the H channel, V channel phase differences. So if you take a look at the pro and con between 2 frequencies, C-band has less noise in the light range. on the other hand, actually S-band has worse, it's more noisy in the light range. So if you take a look at this chart, if you can say that S-band seems has more advantage shown by the blue color here, and C-band has more problem to use in terms of QPE if you take the red color here. But if you perform proper processed data, you should be able to have a similar result. So in the following talk, I would like to talk about how do we use two radar together and give you the same quality of QPE and how to combine them together. So if you take a look at the QPE concept, essentially just try to use the measurement from radar. So I use this example as a ZH and the ZDR. So this information give you the how much rain, and the ZDR will give you information on how big is the rain. So combine these two variables and we put the coefficient ABC here. So the ABC is the empirical coefficient derived from the distributed data. So once you have ABC correct and the ZH and ZDR correct, you should be able to have your rainfall estimation properly. However, in reality, the ABC is not constant. It's changed from case to case, season to season. So the first thing we need to solve is try to reduce the natural variability of DSD. That's the first problem we need to face. And the second problem is the ZDH and ZDR measurement. As I showed you before, all of them have their own issue in S-band and C-band. So we need to correct them and find the problem. So what kind of problem we're going to have? So we have system bias, attenuation effect, very long effect, and we also have some ground cluster contamination. So we all have to take care of all of them. And then once we solve the first and second one, then we can compare which one's better, C-band or S-band. And the fourth one is how do we combine all of them together? Since in Taiwan in the future we're going to have S-band, C-band together, so how do we utilize them in the optimal way? Okay, so the first thing we want to do is we try to derive the coefficient of QPE algorithm for Taiwan. So we collect 8 years of distributed data. We separate them into 5 different type of precision systems. So from spring, Mayu, summer convection, typhoon, and the winter type. So once we have all these DSD for different type, we perform the forward calculation of a dew point measurement so that we can do the linear square fitting to derive 4 different type of the QPE algorithm. So as I mentioned before, because all the measurement, ZH, ZDR, and the KB has their own pro and con in different frequency. So in the following talk, the QPE we're going to introduce is a data quality-based decision tree QPE. That means we will choose the best quality measurement in that case. If it's not good, we choose another one. So we can have a better QPE result. But essentially, we do have 4 different type of result. So then we try to, first we check the coefficient. So this is an example showing the 5 different type of system. We have all very distinct coefficient combination. That means the DSD variability is very strong as we expect. And this is the first step check to see if we can reduce the normalized Roomy square error and normalized mean bias using seasonal coefficients compared to the generalized coefficient. The general coefficient means you don't separate into different types, you combine everything together. So essentially all 4 algorithms showing that the blue line is lower than the red line, which means that the seasonal-based coefficient is much better than the generalized coefficient. But the prevalent test is the ideal test. It just check with the distributed data. So now, and later we want to try in the real case. So for the QPE algorithm, we try to test here. We have 18 cases, 42 hours. They are all heavy rain cases. And we collect the data from 2 radar. This is a C-band research radar, and this is an S-band operational radar operated by Central Weather Bureau. So the procedure we are going to do is we quality control the data on radar coordinate, which we call PPI. And then we perform the QPE over those QC, the PPI data, and then we interpret the PPI radar coordinate data to Cartesian coordinate. And then we choose the lowest available Cartesian coordinate data to perform the 2D QPE map. So this is the result from 4 different algorithms. So the arrow shown here is red means C-band, the blue means the S-band. And this is using the generalized coefficient. If we switch to the seasonal base, you will have improvement quite pronounced. However, you don't see improvement from the ZH and ZDR case, especially in the C-band. It actually gets worse and much, much worse. I will explain later. But in general, most of the case, we will show that the improvement quite pronounced. So let's assuming that the seasonal QP coefficient is better. And then we try to examine how the QC procedure will affect our result. So this is a very complicated chart showing all the QC procedures. So essentially, first thing we need to do is we try to remove those data contaminated by the terrain. So we can perform beam propagation simulation and the digital terrain data, so we can remove those data being affected by the terrain. And then we perform the collateral removal technique. We try to remove those ground clutter contaminated radar echo. And then we perform the attenuation correction technique and the system bias correction technique for all of S-band and C-band radar. And then we perform the QP. So, and we use some technique to perform that. You don't have to worry about what we do. So this is example showing that a C-band radar, and this is the rainfall rate right next to the rain gauge data right next to radar. So you can see that there's no rain and heavy rain, and no rain and heavy rain, two heavy rain episodes. So if you take a look at the bias estimate from the technique, you can see that you can see two. There's a drop here, and the drop here means you have a red radon effect. So let's take a look if we recover all those quality control issues what we're going to have. So first, if we only perform the bias correction, this is the error from C-band and the S-band, and this is the ZH conventional ZR relationship. This is a KTP algorithm. So you will see that if you take a look at this, you will see the C-band is perform worse and higher normalized room square error. But once we perform the attenuation effect, you will see the error drop quite fast. That means we improve the data quality by attenuation correction. And once we further improve the weight radon correction, we can have a similar result. Now you can see the blue bar from C-band and S-band, they have very comparable result. And sometimes you can notice the C-band is actually a little bit lower. So even though C-band has some disadvantage because the wavelength itself, but after we perform proper QC procedures, we can have a very comparable result. And in terms of the different QP algorithm and you can see that all four of these algorithms and solid line and the dashed line represent S-band and C-band, you don't see much big differences, especially ZH and ZDR. And the reason why we have this issue is because in C-band, as I mentioned before, the ZDR has some weight radon effect, which cannot be corrected. And ZH, weight radon effect for ZH, you can correct that, but ZDR you can't. So that's a problem. If you have weight radon effect for ZDR, you have a problem in terms of QB. But you don't have such issue for ZH, KTP, and KTP ZDR. And if you take a look at which algorithm is better in S-band and C-band, you will find that consistently that the KTP ZDR algorithm will outperform the other algorithm. So this is the best algorithm we can have here. So and the most important, and the next thing is how do we use all this information? So it seems to me the C-band and S-band can give you similar and comparable results. So we try to use all of them. So how to combine them? So traditionally we obtain the QPE map from this discrete data because the radar give you every 6 to 10 minutes a scan. So how do we combine them? Because if you have two radars, they don't have a synchronized scan, so they have different measurements. So how do we combine them? So this is traditional approach, which this is the measurement what we have scan 1, 2, 3, 4. So usually we can do different way to do that, depends on what your professor told you. And it turns out you don't know the reality because you don't consider usually the measurement what we have is a Lagrangian evolution of a given location. But in reality, you have Eulerian change given location. But in reality, you have a advection effect and you have Lagrangian evolution because the microphysics and the rain is changing itself. So what I propose here, we try to develop a Lagrangian evolution adjustment techniques. So essentially, we just forward the data from previous scan and backward the data from the next scan and combine them together by some weighting function, so we can have a more smooth evolution of the QPE map. So if we apply this technique, we can further improve all the algorithms slightly, especially in C-band. And the reason why is that is because in this case C-band has longer scanning time. around 10 minutes. So overall, we can, if we take a look in the final, if we combine S and C band together, that means whenever you have a data, you just use it. So you have a best result if you combine S and C band together, which is a black line here. And in terms of all different rainfall intensity, consistently better than using only single radar. So this is a quick summary. And I would like to talk about a little bit that, so the VOLT project, we installing a Pasivo, which is a distrometer in UP Las Bonia, and thanks to all of them help, and some of them are here. So this is a very preliminary result that we try to compare the data with the radar very close to the university, and this is the result showing that this is a time series of range offset distribution. This is 1 day, and this is the corresponding the vertical profile precipitation. So you can see the you can see what happening of the precipitation and what the range offset looks like. So that's all my talk. Thank you.
Okay, thank you. Thank you, Professor Zhang. Okay, now we are going to the discussion. Yeah, any question? We have 4 speakers. No question? I have 1 question. Okay. Margarita? Okay, I have a question on Margarita. As we know, we can divide the potential of the landslide to be high susceptibility, moderate, and low, and others. Why? I have a question. As you show the number in your presentation, the largest number of landslide in last year does not in high susceptibility area. Yeah. I just curious why.
Okay. The landslide not automatically fall in the maximum or the highest susceptibility. Maybe due to the assignment of the centroid. I think this go down, please.
Yeah, you can see.
Yeah, this the episode 28.
Yeah, yes.
Okay. This one, the slope of centroidal polygons. I think this will be the basis. So for the slope assignment of the slope, it's an auto assignment of slope. It depends to the centroid. So it falls in the 28 to 33. I think the highest slope or the most among the table. So basically, I think this one, it depends to the geology, and also at that time the area is already saturated. So the geology is a little bit how do you call this? Sorry, I forget the term. So it's highly saturated is the geologic material. I think the landslide falls in the rolling slopes for these identifications. Okay.
Okay, thank you.
Okay.
Yeah, I try to understand because
Yes, sir.
because sometimes when we're talking about the susceptibilities, it does not account the triggering factors. Okay, only based on the historical data. Yeah,
Yes.
maybe look like even the landslide may have different accelerations or movement. I don't know. Yeah, I'm just curious about that. And any question on her? Oh yeah, Dr. Yin.
Thank you very much for your talk. For this slide, I'm just curious why the distribution of the landslide versus the slope range is normal distribution, because we see some case in Hokkaido, Japan. We see when earthquake occurred, so the peak of the mountain just sliding more seriously than other places, because in the high mountain they got more more crack than other lower lands. So why like this one? it should be higher. I mean, higher landslide, more landslide in the higher slope areas.
Okay. So, okay. Okay.
So is it possible that because of the, like the Professor Zhang said, the rainfall distribution, because the rainfall just falling down in the middle slope range areas?
Yeah, that's the one thing I'm thinking, because normally if you compare the rainfall and the seismic failure of the slope, normally the rainfall is on the moderate or maybe a base of the area. But for the seismics, normally it falls in the highest peak or the top of the ridge. Sarat and I also are discussing about the result, because we're thinking that the possible reason maybe is because of the slope identification is located normally in the high, but if you check for the slope, it's becomes low slope, meaning for example for the ridge crest, normally it failed the ridge crest, but if you check the slope, it somewhat point to the low slope degree.
Okay.
Yes.
Yeah. Oh.
I have a question for patrons. Okay, Dr. Patrons, about this mountain McKinley landslide. In your talk, that you mentioned that the mountain McKinley Forest Reservoir, there's caused by the typhoon, right? Yeah, typhoon from the east. So most of the landslide should occur on the eastern slope. Is that right? You have any data to show that the rainfall distribution around this mountain McKinley, because it's like a bell shape, right? It's a bell shape, and currently, I think Pagasa is using the Targeta radar to monitor this area, but Targeta is on the west side instead of east side. So how you get the rainfall information on the east side of this mountain?
We have station nearby, which is the.
Can you show us the area? Yeah.
We have a station inside the university. So one of the Institute of Plant Breathing, they have rain gauge. So they have given us the rainfall data, but actually the rainfall during that time is very low. See, it's around 300 millimeters only. So, and it could be a compounding effect. So it's a low intensity but a longer duration of rainfall. It's about 4 days, or even before that. There are other like small systems like monsoon systems that are causing a lot of rainfall. So probably the soil in the area is already saturated at that time. Even though the intensity is very low.
So during the summer monsoon season, you will have more heavy rain on the west.
Western should be the western
so
side.
both sides actually has a heavy rain, a chance. Is that right?
Yeah, there is a lot of rains also on the
debris over there.
other side, northeastern side.
Yeah. Okay. Thank you.
Yeah, I have a question on you also. Okay. You pick up 8 key factors on landslide analysis. Okay, key factors. But how do you decide the weighting factor? Is that a weighting factor for the same, all areas the same value? Weighting factor, weighting number.
The weight, the percentage.
Yeah, percentage.
So we have to first rank the, for example, lithology. So for Northwest Mendoros, we have 5 lithologies. So we have to rank those lithologies depending on the occurrence of landslides. So these are supported by past landslide events. and also the properties of these rock materials. So we have a lot of landslides in the orange one, the other side. So we have a lot of landslide in the sedimentary rock, so sandstone. So these are also these areas with high susceptibility, the orange one, and with a lot of landslide occurrences. So we rank those according to their effect on the susceptibility to, according to their susceptibility to landslide. And then we have to compare different factors in the AHP. So comparing lithology versus slope, and then we're using the numbers 1 to 9. So one being the lowest effect and 9 being the highest. So we have to compare lithology versus slope versus elevation. So comparing all the parameters with each other. And then at the end, we can get the weight of the each parameter.
So that means the different area have different weighting factors.
Yes, that's...
Why? I'm just curious, the same problem also. Why? Triggering factor. Without considering triggering factors, the potential always is potential only. We cannot use that for warning because the triggering could be moved. Geological or morphology is always the same, keep the same. But the triggering factor could be variation, different time and different season, especially when you're talking about the climate change. It's talking about the changing of the triggering factor. So I just curious because some people ask me to review the paper. Why? I was curious why without the input the triggering factor is, for example, the large of the rainfall, the intensity of rainfall always is not considered for the susceptibilities. Yeah. I just curious on that. Any other question? I think we have a hot discussion.
Dr. John, I think I just want to note that I've read the phrase from Dr. Lucio's presentation that no one size fits all. So I think there should be a different treatment for landslide susceptibility assessments in different areas. For example, in the Philippines, we should have a different susceptibility assessment for volcanic terrains and for another like sedimentary rocks laden areas. So different susceptibility treatments for different maybe lithologic types.
Yeah. And you want to?
Methodologically, the analytic hierarchy process is subjective. You ask one expert, he gives you one answer. You ask another expert, another answer, and what everybody's correct in this case. So, what is important as far as the method is concerned is consistency. And it allows you to be in error only up to 10%. You should be consistent in your decision, in your weighting, up to 90%. But methodologically, that's how it works. So the rigor of the method is evolving. But the purpose of getting expert opinion, I think it's crucial.
That's good. You could comment, yes. And we still have two Taiwanese speakers. Anyone to have a question on these two guys? Yeah, to be a moderator, it's my job. I got to ask one question. Okay, I want to ask the Professor Zhang. Yeah, because you have a rainfall model, okay, and the coefficient ABC you're talking about, it's dependent on different location, different situations. If the coefficient is not fixed, how can we use that? Or at least we need to know to the range of the variation. Otherwise, how people can trust the result? If the coefficient changed, then the result is changed.
Yeah, it's perfect question. So usually what we do is, so in my talk, I actually consider it as a generalized coefficient or a seasonal based coefficient. So you can put it that way, that generalized means you don't consider any seasonal change. So a seasonal coefficient, that means you consider seasonal change. So there's some approach we can actually try to do case-by-case coefficient. That would require to examine the precipitation structure case by case. So that's also one part of my work. So what we're trying to do is we can use the radar data to identify the precipitation structure. For example, how deep is the convection or how strong is the convection? So we can relate that information to the DSD. So that is theoretically that should be able to give you the case-dependent coefficient. And in reality, it's still not enough. But we try to reduce the error step by step. So we're still working on that. Okay. And in terms of the uncertainty, we definitely can give you some range. So we can give you a QP uncertainty for generalized coefficient, signal coefficient, and case-by-case coefficient. That's something we can provide. Yeah.
Oh, yeah, I got it. Yeah, thank you. Yeah, you look like a hydraulic engineer. When you're talking about the minus M value, okay. For engineer, you got to decide the one value. And my senior professor told me, ask the same question on him. How did you decide the minus M value for the natural rivers? He said, by his hand. Okay. He said, when I'm talking about the value, you got to trust me. Yeah. So if we are famous, look like the Professor Zhou, okay, give you a number. Then he said, okay, just decide use that value. Yeah, just use it. And we have another speaker. So I have a question also. Or other people want to ask a question on him? Or no? I ask, okay. For the debriefer event, you take the data from the debriefer event, the same event. Why? The measurement from the geophone or semi-monograph, the result is close but not the same. Okay, still have some difference. But because the signal should be the same. Why? When you catch that by different tools, the results still have some difference. Why? I just don't know why.
Because there are different location sensor. Okay. Yeah. So the different information.
Did you check if we put the same location?
Maybe in the future we will move the location, the same location to detect again. So next year maybe we can move the sensor location together.
Okay. Oh, it's different location, so hard to compare.
Yeah. Upstream and downstream.
I understand.
Yeah,
but for
upstream and downstream. Yeah.
Okay. Good answers. Maybe Professor Yin, Dr. Yin. Yeah. He has a very good experience in measurement also.
Thank you very much. So it's a very good question because we have tested different kinds of sensors, detect the ground vibrations generated by debris flows, especially in the same site, because different sensors has different response curve. So as far as I know that different sensors, they enlarge different frequency range of the amplitude. So in the same place, even the same place, the same event, they got the different the response about the spectrum. So that depends on the target vibration signals. If we want to capture the lower frequencies, which can propagate longer, so our purpose is to get the signal as early as possible. Then we use the seismometer. If you want to capture the higher frequency, we know the broadband of the vibration signals generated by the rifle, then we turn to the geophones. So that's the spec of the different sensors.
I mean, we need more study again.
Yeah, I think so. Of course.
That's research, always research. Okay, let's stop here. We are give the big hand for our 4 speakers again. Thank you very much.
Ladies and gentlemen, thanks to Professor Zhang and his insightful question. Give him a big hand. Okay, because we have a little delay, so I suggest we have a coffee break until 3:15. So please enjoy the coffee break backward, and please come back in time. Thank you.